Hi folks, Mr. Ackerman here. Thanks for watching. Topic of today's video is basic electric circuits. And maybe one of the first things that you notice is that in the learning goals and success criteria, we are, and also in the homework schedule rather, we are covering quite a bit of ground here. And the reason is twofold. One, at the time that I'm recording this video, we're kind of in the abbreviated final unit because with bad weather and whatnot, we've run out of time at the end of the semester and we have to go a little bit quicker, so we've got to combine some lessons. And the other reason is that a lot of the ideas that we're going to discuss you covered in grade 9, if you recall, back in the electricity unit, and they're all kind of related. So even though it's going to sound like a lot, they're all going to sort of come together very shortly. And you see lesson 1A, 1B, 1C, learning goals, success criteria, and a little snapshot here from your schedule. So here's what we're covering. I'm going to try to go quickly so that the video doesn't go too long. If you find me going at a faster pace than normal and you need to stop, then just pause the video and rewind if there's anything I say that doesn't make sense. In a nutshell, what we're going to be talking about is electric current and voltage and resistance and power. So all of that in electric circuits. Here we go. Okay, so first of all, take a look at this picture. It's a picture that many of you probably have seen or seen something like it before. It's an electric circuit. Why is it so important? Why do we need to study this? Well, first of all, if you look around you, everything seems to be connected to electricity. All of our gadgets, our smartphones, our computers, our televisions, even the appliances in our home, the cars, everything is so high-tech and based on or working off of electricity. And they're all using very complex circuits to do the jobs we want them to do. A lot of the things that are in this picture here, which I got off of Google Images, you'll recognize possibly from grade 9. For example, down here is something called a resistor. You learned about those in grade 9. We're going to cover them again. Here's something that looks like maybe like a resistor, but it isn't quite. It's called a capacitor. It stores electric charge, and it's a very important circuit element. And then, of course, there's these things here. These are called integrated circuits. They are based on semiconductors, which is a kind of substance, an element rather, such as silicon, as an example, which you may have heard about in the past. They're on the so-called staircase of the periodic table of the elements, and they have some interesting properties. One thing that I think you should all strongly consider if you're going into science and physics is that if you want to have a career that deals with electronics, your future looks pretty bright from this point because obviously everything is just getting more and more technical. And if you're one of the people designing and studying these things, I would guess that you probably have a good shot at a well-paying job well into the future. So consider that. Anyway, let's get started by talking about some of the things you need to understand in order to understand these circuits. So here we go. First off, think way back to grade 9, or even maybe earlier when you were a little kid. Ever remember rubbing balloons in your hair and your hair stood on end, and the balloons, you were somehow able to pick up little pieces of paper with them, or you could even stick them against a wall and they would stay on the wall as if they had been taped there. Well, here's a picture of two balloons which have been charged by rubbing in some fur that you see down here. They're both hanging from strings from a retort stand, and what do you notice? They are hanging at an angle. It's as if they're repelling one another. And in fact, if you think about forces, then that is what's happening. They are pushing each other apart. They are what we call repelling. We could write down that these are forces, like this, the symbol F. The interesting thing is, why are they repelling? Well, do you remember back when you were a little kid, maybe learning the law of electric charges? That's the one that says opposite charges attract. And it also says that like charges repel. Remember that one? There's something similar with magnets, and we are going to study that later on in this unit. Remember with north and south poles of magnets, how the like poles repel and the opposites attract? Same sort of thing. In fact, electricity and magnetism are related, but we're going to start off by talking about electric charges. So when we talk about opposites attracting, we're talking about positively charged and negatively charged things. If we're talking about like charges, then we're talking about two positively charged things or two negatively charged things. So since you see there's some sort of repulsion going on here, these balloons must be charged with the same kind of charge, either both negative or both positive. It's not entirely clear which one it is. Now, how do things get charged? Well, obviously one way is to rub these in your hair or rub them in fur. Why does that charge them? Think back to grade 9. Do you remember something called the electrostatic series? It was a list of substances that if you rub them together, they would become charged. Basically, one of the substances that you are rubbing has a stronger hold on its electrons than the other one. And so when you rub these substances together, one of them grabs electrons from the other. The one that got the extra electrons becomes negatively charged. The one that lost the electrons ends up positively charged, because remember, it still has protons inside of its atoms. So the idea here is that electrons are transferring from one object to another. In the case of the fur and the balloons, probably the fur lost electrons, and so it gave electrons to each of the balloons, and therefore the balloons are probably, I'm going to guess, negatively charged. Now, if that's the case, we might ask ourselves, well, how many electrons jumped from the fur onto the electron? The answer is probably countless electrons, more than millions, maybe billions of electrons transferred. It's not at all clear. You'd have to know how much rubbing happened as well as some other details. However, if we know the charge on one electron, we could figure out the total charge. Well, the electron is a particle which cannot be broken down any smaller than it already is, and therefore we call it an elementary charge. The charge on an electron, which we can write as the letter Q, Q as in quantity of charge, QE for charge on an electron is negative. Remember, electrons are negative, and the value is very small. It's 1.6 times 10 to the negative 19, and the units are C, or coulombs. Is all this coming back? You did it in grade 9. I hope you remember some of this. That's a really tiny charge. Well, suppose 1,000, or let's say even more. Let's say 1 times 10 to the 6. Let's make it 1,000,000 electrons transferred from the fur onto one of the balloons. Well, if that was the case, then what is the total charge on the balloon? Well, we could write that with the letter big Q, and we could write it as n, the number of electrons, times the charge on an individual electron. So we could write something like 1 times 10 to the 6 electrons times the electron charge, which is negative 1.6 by 10 to the negative 19 coulombs, and that would give us the total charge on the balloon. I think that's going to come out to negative 1.6 by 10 to the negative 13 coulombs. So still a small number, a small amount of charge, 10 to the negative 13, however, enough that these two repel one another. All right. Now, speaking of the repulsion, how do we calculate the amount of actual force that is repelling or attracting two charged objects? Well, for that, we look to something called Coulomb's law. This is a formula that tells you the electric force, Fe, between two charged objects. Now, I'd like you to pause the video for a moment and think about what might be affecting the force on these two balloons. What factors might be affecting that force? Pause the video and think about it, and then come back. All right, you're back, and what did you think? Well, I certainly hope you thought that the amount of charge would matter. So we would not be surprised to find the letter Q in this formula. But there are two objects, so the charge on one of them and the charge on another should be part of this formula. What is another factor? Well, if you've ever played with balloons like this, or if you've ever played with magnets, you've probably noticed that the farther apart they are, the weaker the force, and the closer they are, the stronger the force. So what we do is we put the letter D in the denominator of the formula, because bigger denominators, farther apart distances, mean lower charges. And actually, if you study this in detail, you find out that the distance has to be squared. Finally, to finish off, there's a constant which multiplies this value, and the constant in physics is given the letter K. The K value is a very large value. The electric force is actually quite strong, so it's got a large value here of 9 times 10 to the 9. The Q values are the charges on the individual objects that are experiencing force, so charges in coulombs, and the distance, d, is between, b/w, between the centers of the two charged objects, and that would be in meters, as it normally is. Now, force, of course, is in newtons, so let's get back to this constant here. We need to get newtons out of this, so there's going to be a newtons in there. There's meters squared in the denominator, so we need meters squared in the numerator of this constant, and there's coulombs times coulombs in the numerator, that's coulombs squared, so we need coulombs squared in the denominator. If you sub this in, all of the values will cancel out, all of the units rather will cancel out to give you newtons as your force. And so what would be an example? Well, suppose each of these balloons had this much charge that I calculated above here. What would be the force? Well, you could calculate 9 times 10 to the 9, the constant, times the two charges on the balloons, which I'm going to pretend is this value, 1.6 times 10 to the negative 19. And of course, there are two of those. I'm going to pretend that it's the same charge on both balloons. And then we divide that by the distance between them. Now, what's the distance? They give us a meter stick here, so you could probably guess, I don't know, maybe that's 25 centimeters, so 0.25 meters, and you'd have to square that. Now, let's see what force we get. I'll just pause the video here and do it, and you can do the same. All right. Okay, folks, and we're back here. First of all, while I was doing the calculation, I noticed I got a super tiny number, and that's because I made a mistake here. I meant to use this number here as the hypothetical charge on the balloon, so these should have been 13 right here, and so should this one. I went ahead and did the calculation, and I still came out with a number which I feel is a little bit too small, just about 3.7 times 10 to the negative 15 unit, well, let me try that again, 3.7 by 10 to the negative 15 newtons. Of course, that's a really tiny force, but remember, I was just playing around with numbers here. I didn't know if this was the exact number of electrons that transferred when you rub the balloons in the fur. I'm guessing that because this force is so tiny, it would not likely repel each of the balloons this much, and therefore I'm going to assume that I probably was wrong about the number of electrons that transfers. It's probably much larger, and so you'd get a higher force. But you get the basic idea. This is how we calculate the force between two charged objects. All right, moving along. So the next thing we're going to do is talk about what happens to electric charges inside of a circuit. As you know, electric charges move through a circuit. You learned this in grade 9, and this is what gives us the ability to, let's say, light up a lamp. So that's what's shown in this diagram here, which is taken from your textbook Physics 11 by Addison Wesley in chapter 12. So what do you need to do to get an electric current to flow? Well, you got to connect a battery or some power supply to your device that you wish to operate, let's say a lamp. And if you connect the positive terminal all the way around, maybe there's a switch here, all the way around to the negative terminal, current will flow. Now your textbook and I are going to point out that there are two ways to look at the current flow. One way is the way you learned in grade 9, which said that electrons leave the negative terminal and they flow around to the positive terminal. Now that is one way of looking at electric flow, the direction that negative charges flow. And the green arrow here shows you that. However, mathematically it's identical to say that electrons go one way or hypothetical positive charges go the other way. Now what are these hypothetical positive charges? There are actually not positive charges flowing through an electric circuit. The positive charges that we know about in atoms are locked deep within the nucleus. They are the protons, and they're not the ones that move. If you remember from your chemistry class, it's the electrons in the outer shell of the atom that do the moving. So while the green arrows show us what's really going on, which is called electron flow, at the time that physicists were studying this stuff, back in the 1800s, they didn't know what was flowing, and they assumed that charge went from the positive terminal to the negative. How would you think about that? Think of the positive terminal as being higher up, as in if you were dropping a mass to the ground, it would naturally drop from a higher level to a lower level. You can think in similar terms with electricity. think of the positive terminal as the higher terminal, and the flow of current, the positive current, which is given by the red arrows, this is, by the way, called conventional current, it goes around to the negative side. That's how we're going to do things, and that's how most professionals think of electricity. Now that you understand what electricity is all about and how we show its direction, let's talk about electric current. What is the formula for measuring the amount of current flowing? First of all, electric current is given the symbol I. And I don't know why it's given the symbol I. I believe it has to do with the word for current in French. I think it starts with the letter I. I could be totally wrong. Maybe someone can check that out for me. However, the current is defined as the total amount of charge, so I'm going to use capital Q for that, divided by the amount of time that it flows for. If 1 coulomb of charge flows through a circuit, and if the time that it takes it to flow past any given point in the circuit, let's say right here, is 1 second, then we have, on this side of the formula, obviously 1 coulomb per second. But a coulomb per second is given the name amp, 1 amp, or 1 ampere, which I believe is a French word. That's why I'm going with my French guess for what the letter I stands for. The letter that we use for ampere, of course, is A, and this is what we mean by electric current. So, for example, let's say 23 coulombs flows past a certain point in a circuit in half a second, then what would be the current? Simple. We would plug in to the formula I equals Q over time, and you do 23 coulombs divided by 0.5 of a second, and that would, of course, give you 66 coulombs per second, which would be 66 amps that you would write this way. It's really simple. And that is the first fact of the video, to memorize the formula for electric current. Total charge flowing divided by time past a certain point in the circuit. Now, how do you measure electric current? Do you sit there and count electrons and see how many coulombs there are in a certain amount of time? Obviously not. There would be countless electrons. However, what we do is we use something called an ammeter. And an ammeter is an electric device that looks somewhat like this diagram here, also from your textbook. And how do we set it up? Well, if we take this particular circuit, which is shown here, the light bulb is just in a different position, all you do is you get those electrons, or rather the positive charge that we're imagining is flowing. Remember, we're using conventional current from positive terminal to negative. What you do is you make it flow right through the ammeter. You connect the positive side of the battery to the positive terminal of the ammeter, and you connect the negative side to the negative terminal of the battery. And that's it. You just make a nice little circuit so everything's going in a loop, and that will give you the current. You'll have to read the ammeter, and we're going to practice that in class. So that's very straightforward. All right, moving on. There's another topic that we have to discuss in terms of the flow of electric charge, and that is what actually causes the charge to flow in the first place. Back here I talked about what the flow of charge is and how we calculate it and how we measure it, but I didn't tell you why electric charge might flow. The only hint I gave you was that if you think about gravity and you drop a ball from a really high height, it goes down to the lower height. And the thing that I asked you to think about there was the positive terminal being like a high height and the negative terminal being a low height, and there go the red arrows, the conventional current. Well, now we're going to study something called electric potential or voltage, and hopefully this will explain to you why electric charge flows. First off, another diagram from your textbook. 2 cylinders filled with water connected by a tube. I have a question for you. What would happen if you poured a little bit of extra water onto this side? Well, answer, the water level would rise, but because these are connected, if I open up this clamp, what's going to happen? This water will go down. This water will come up. How much will this scenario play out? How long will the water keep flowing? Answer, until the 2 levels are equal. Once they equalize, which would probably be somewhere in the middle, once they equalize, there will be no more flow. What does this have to do with electricity? Simple. When we pour the extra water in here, we raised the water level up. This was at what we call a high potential. The water down here was at a lower potential. And therefore, if we opened up the clamp, water flowed from high potential to low potential. It flowed and continued to flow until there was no what we call potential difference between the two sides. Okay? If there's no difference, there's no flowing. No difference is kind of like no battery or a dead battery. A big difference is like a charged battery. Now you know what is pushing the electrons or the charges through this circuit. It is that the difference in potential that the battery supplies is doing that. How does the battery do it? Do you know how batteries work? Well, there's chemical reactions that occur in here involving electric charges, of course, chemical reactions, chemistry, the sharing or swapping of electrons from one substance to another. So it's not a surprise that a battery can provide the energy to do this. And of course, it relates to gravity through this diagram here. So how do we measure, or how do we calculate rather, the voltage? Well, voltage is obviously an energy idea, and it's a charge idea. The formula for voltage, and we use the letter capital V, big V like this because we don't want to confuse it with speed, V. V is equal to the energy done to move charge. So it's energy divided by charge. Energy is measured in joules, and charge is measured in coulombs. So a volt is a joule per coulomb, or a volt. As you've, I'm sure, heard when you go and buy these batteries, you read things like 9 volt or 1.5 volt. Okay? So a simple example might be if a battery and its chemical reactions use up, let's say, 20 joules of energy to move, let's say, I don't know, 5 coulombs of charge, then what is the voltage of this battery? It's E divided by Q, which is going to be 20 joules divided by 5 coulombs. That would be 4 joules per coulomb, or 4 volts. Okay? And that is the second fact of the video, this formula. I'd like you to memorize that. The formula for voltage, which is E over Q. All right? Next up, how do you actually measure voltage? Do you sit there and measure energy and count charges? No, just like with the ammeter that we had here, this time we're going to use a voltmeter. How does a voltmeter work? Not exactly the same as an ammeter. What you got to do with a voltmeter is you don't make the current flow through it quite like you do with an ammeter. With an ammeter, see here how we made the current go right through it. Here was the flow going this way, this way, this way, this way, through the lamp, this way, this way, this way, through the ammeter, this way, and back to the negative terminal. What we're going to do with the voltmeter is a little bit different. Let's follow the flow here. Out the positive, through the lamp, and what happened there? We didn't go through the voltmeter. Well, what you do is you connect the voltmeter alongside the lamp. So there's actually 2 paths for the charge to flow. One is the red path through the lamp, and the other is this blue path through the voltmeter. In other words, it's what we call a parallel path. Do you remember that from grade 9? Parallel circuits and series circuits. A voltmeter is connected in parallel, but an ammeter is connected in series with the circuit. So getting back to this, you connect the voltmeter in parallel to find out the potential difference, there's that word difference again, the difference from the starting point, which would be where you make the first connection, to the final point, where you make the other connection. Positive side of battery with wire closest to positive side of voltmeter. Negative side of battery with wire closest to negative side of terminal. Okay? And the before and after nature of this measurement is kind of like this with the water example, higher and lower potential. All right? Hope that makes sense. If it doesn't, then just rewind the video, play it again. Soon it will sink in. And so to finish off this first set of slides that I have for you, what we next need to do is to see how do you take a picture like this, which can get awfully messy, and convert it into what's called a circuit diagram. Well, a technical circuit diagram, and I'm just going to move this over a bit, these images once again from your textbook. Let's see what happens. A battery, such as you see here, is written like this, a series of short and long lines. The short lines are the positive terminal, the long lines are the positive terminal, and the short lines are the negative. Wires are written as lines, and they often meet at right angles, so they don't have all this messiness here. Connections are just shown by one wire touching another. Here's a switch that can turn on or off, or sorry, rather open up or close the circuit and allow either prevent flow from charging when the circuit is open, prevent charge from flowing when the circuit is open, or allow it to flow when we close a switch. Ammeters, which go directly into the circuit, are drawn directly into the circuit. Light bulbs look like this curly circle symbol here, and a voltmeter, which measures before on the high side and after on the low side what is the energy per charge, the potential, they are drawn like this. So you see the parallel nature of the voltmeter versus the series nature of the ammeter. All right, there are other circuit elements. For example, there could be motors or generators or things called resistors. You can look these up online. We will encounter them shortly. However, this is a very basic circuit, and hopefully that makes sense to you. Let's do one simple calculation to finish off this first set of slides. Suppose that a 9-volt battery delivers 4 coulombs of charge. Part A, how much work is done? Remember, work is the same as energy on the charge by the battery. So first off, we're going to use our memorized equation that says energy divided by charge, or since energy is work, you'll also see this. So we can calculate that. We've got 9 volts equaling a certain amount of work divided by a charge of 4 coulombs. We can solve for the work done. 9 times 4, that's going to be 36 joules of energy. That's part A. Part B, how long was the battery used if the current was 1.5 amps? So this time they give you current, and they ask you how long the battery was used, so we got to talk about time. Remember the formula? You have to memorize this. It's one of the facts of the video. Q over delta T. So we're going to sub in 1.5 amps equaling a charge of 4 coulombs divided by the time. Time is going to come out to 4 divided by 1.5, which I think is somewhere around 2.67. So we get 2.7 seconds sig figged. All right, so we've now covered some of the basics. I'm going to open up a new set of slides, and we're going to conclude with the second half of this video. So stop that there, and we're going to open a recent image. This will be number 2. Here we go. All right, so next topic to talk about in an electric circuit is something called the resistance. Also, you studied this in grade 9. Do you remember what it was? Here's the idea. When a battery or other device that creates a potential difference is connected to a circuit and allows electrical current to flow, the question becomes how much current will flow? Like if you put a 1.5 volt battery into your flashlight, how much will the flashlight light up? Will it light up at all? What if you put 2 of these in so that you had a total of 3 volts? What if you rewired it and connected it to a 9-volt battery? I think you know that as the voltage went up, so as voltage increases, the current will likely increase. That kind of makes sense. But why does that happen? What exactly is the relationship between the two? Well, it all depends on something called resistance. Resistance is given the symbol R, not surprisingly, and if you remember, it's measured in ohms. The symbol for ohms is the Greek letter omega, which looks kind of like a horseshoe. Oops. All right, and so what is this thing called resistance? Well, here's the idea. Almost everything has electrical resistance. Batteries, light bulbs, wires, things that are actually called resistors, integrated circuit elements, computer chips as they're called. What is it about them that resists the flow of electric charge? What is it about them that when you apply a certain voltage, you only get a certain current? Well, the answer is that the electric current, the charges, have to flow through the device. If it's a battery, then here's the positive terminal, here's the negative. We normally connect this, let's say, to a light bulb. And of course the charge flows positive, positive, positive through the light bulb, actually goes up through this thing called a filament in there, and then down and then back. And of course the charge now has to make its way up here. Even going through the battery, there will be some resistance to its flow. Going through the metal here, going through the tungsten filament here, same thing. Wires have resistance. Things that are called resistors are things that can be put into circuits to control the amount of current. They obviously have resistance. And even the things that you want to do things for you, like computations, like a computer chip, has resistance. What is it that causes that? Well, remember that all matter is made up of things we call atoms. And the atoms, in the outer layers of these atoms, are vibrating electrons. Now, remember, we talk about the direction that positive charge flows, even though we really realize that it's the electrons that are going the other way. It is the electrons that have to get through the circuit elements, as we call them. And when they do that, they bump into the atoms that are in the way. And that is what resists their flow. Basically, every time they collide, it costs them some energy. And so we basically look at that as saying, for a certain voltage applied, I'm only going to get a certain current. What is the relationship? We're going to look at that shortly. But I do want to point out to you that not everything has this property. Almost everything has the property. There's a really neat set of substances that are called superconductors. You may have heard of this. Superconductors, as their name suggests, are electrical conductors that are so good at it, they do it with a resistance of 0. If you can imagine, when those electrons try to move through things like wires, they bump into the atoms along the way and they cause a lot of friction. They heat up. And as the substance heats up, there's a lot more vibration of the atoms that are in the substance, making the resistance go even higher. Well, then it makes sense that if you cool something down really, really low, the resistance should drop. And that is true. Most things, if you cool them down, and this is showing the temperature getting cooler towards 0 Kelvin, absolute 0, if you cool them down, the resistance drops. But most substances, most metals, let's say, that are not superconducting, will reach a certain resistance at 0 Kelvin, and after they get to this point, they can't get any lower resistance because you can't go any colder. But there are some substances that all of a sudden, at a certain temperature, Tc, called the critical temperature, which can be very low, at this point, they suddenly lose all their resistance. They have 0 resistance. And then weird things start to happen, and amazing, neat things that could potentially hold the key to very efficient use of electricity. So that's all I'm going to say at this point, is that you can get 0 resistance if you're dealing with a superconductor below its critical temperature. If this interests you, you should definitely look into it. It certainly holds some promise for your future job prospects if this stuff interests you. Anyway, let's move on now and look into resistance in more detail. We now take a look at something you also learned in grade 9. Remember Ohm's Law? Someone by the name of Gregor Ohm, this is who this is attributed to, and the idea is as follows. We're going to set up an electrical circuit, and the electrical circuit, sorry, just let me pause the video for one. Hi folks, Mr. Ackerman here. Sorry, I accidentally stopped the previous video, so I'm going to have to do this in 2 parts. This is the continuation. We were talking about Ohm's Law, which is fact of the video number 3, and we were going to look at the formula that relates the electrical resistance to the amount of voltage and the current that will flow in a circuit. So let's do a little mini lab in our minds here. Here's the setup. This image is from Google Images. You're given a power supply, some wires. This is an ammeter, and this is a voltmeter. And here is some strange device which I've magnified here so you can see it. These are resistors, which I showed you in one of the earlier slides. And remember, you use these in grade 9. The idea is to be able to use 3 different resistors, or even 4 different resistors in this lab, so that you can vary the resistance and use whatever power supply, whatever voltage you want, and measure the current. So here's what we do. We set up a circuit diagram that looks like this. We've got our power supply, which is right here, and it's got a line through it. This is a new symbol. This means variable power supply, which just means we can turn the dial that you see right here and vary the voltage. And next up, the strange thing that you see is this sawtooth symbol. This, of course, you learned in grade 9, is a resistor, and it's given the symbol R. Now, what we're going to do is we're going to connect a voltmeter across the resistor to measure the potential difference. We're going to use an ammeter to measure the current. And so we would plug with these wires here, we connect them to the power supply, send the current through one of these resistors, and then we would take a reading of, for whatever voltage I choose, what is the corresponding current? And you could do various measurements. You could keep turning the dial on the voltmeter and get a bunch of readings here, and then you'd use the ammeter to measure the current like this, and then you'd plot them. You would plot, however, the voltage, which even though is the independent variable here, you would plot it on the vertical, and the current, the responding or dependent variable, you'd plot on the horizontal. I'll explain why in a moment. If you do this, you'll find you get a straight line. As voltage rises, so does current. And that's not a surprise. More voltage should lead to more current, or more current should be associated with higher voltages. But this is a line that looks like y equals mx, where m is the slope. The y-intercept ends up being 0. Now the y value is voltage, so we write V. The x value is current, so we write I. And the slope is something that we just measure. If you do rise over run, you'll get the slope. That's not anything new. The interesting thing is, if you measure this slope, you will find that the slope equals the value of the resistance on whatever resistor you had plugged the circuit into. And so we come to realize that V equals R times I. And this is what we call Ohm's law. That is the third fact of the video. I'd like you to memorize this formula. V equals Ri. Okay, just going to pause the video for a sec, this time properly. Okay, sorry about that, folks. I just had to deal with something, and I'm back. So what did we find out here? We were talking about how V equals Ri, the formula for Ohm's law, which I'd like you to memorize as the fact of the video, number 3 fact of the video. Now, let's have a look at how we can do some applications here. Now we can start to look at how resistance affects the current that you get when you apply a certain voltage. Let's say I take a 9-volt battery, or actually no, not it. Yeah, sure, why not? Indecisive here. Here's what a 9-volt battery might look like. And I'm going to connect it. One terminal is positive, one is negative. I'll attach it to, let's say, a light bulb, probably a little light bulb. And I'll also connect it to an ammeter. Okay, and what I'm going to do is measure the current with the ammeter, so I'll get a value for I. Let's say for whatever reason I get, I don't know, 0.3 of an amp, also known by the way as 300 milliamps. Yes, it's true, metric prefixes are back, you better learn them. I know I keep saying that, make sure you have. Here's the voltage here. And so what would I find if I used the resistance formula? Capital V equals R times I. And so I would know that 9 volts is giving me a current in this, for this light bulb, of 0.3 amps. So I write this. And I can calculate the resistance. 9 divided by 0.3 equals 30. All right? So I get 30 ohms. Now, what I'm going to ask you to consider now is the following. Suppose I connect this same light bulb, which I now know has a resistance of 30 ohms. Suppose I connect it to one of those smaller batteries, you know, the kind that has just the one terminal up here, and it's got the other terminal down there. This might be like a AA battery. Okay, so it's got a positive here, and it's got a negative there. I'm going to connect it to the same light bulb, and I'm going to put it through the ammeter. So we get something like this. By the way, I just realized I made two positive terminals up here. It must be something that I ate. Okay, there we go. So here's the light bulb. What do you predict is going to happen? I'm now only using a AA, which only has a 1.5 volt potential difference. I've got 30 ohms here. How are things going to change? Less voltage for the same resistance. Less push to get through the same resistance. Answer, the current should drop. Let's see. V equals Ri, so I equals V over R with my 1.5 volts divided by the 30 ohms. What do I get? 1.5 divided by 30 is in fact a much smaller number. This time I get 0.05 of an amp, which if you convert to milliamps, remember your metric prefixes, learn them folks, 50 milliamps. So it's true. The same resistance resisting less electric potential will resist current, give you a lower current. Okay? And so there's a calculation comparison involving Ohm's law. Let's move on. Now remember way back, actually way back here, we talked about how almost everything has electrical resistance. Well, that's because charge is going through everything in an electric circuit. Even the wires, which are made of metal, which are conductors, which should give us a pretty low resistance, even they've got electrical resistance. We can calculate the electrical resistance of a wire. Here's how we do it. I want you to try to consider that electric current is trying to flow through this wire, and I'll do that with an arrow and the letter I. All right. What are some of the factors that are going to affect the current, that are going to slow it down, resist it? Pause the video if you like, and see if you can brainstorm some of them, and then come back. Okay, you're back, and what are they? Well, first of all, one thing you might notice is that the bigger, or rather the wider this wire is, the thicker it is, the easier it should be to get through. The reason for that is the same reason it's easier for you to get down a wide hallway in our school than it is to get down a narrow hallway. So the thickness, or really the radius of this circle that you see here when you chop a wire, the thickness, the radius, matters. In fact, it's what we call the cross-sectional surface area. The area of this circle, which is pi r squared, the larger the area, the less the resistance. Keep that in mind. Now here's another thing. The longer the wire, the more collisions there will be with the electrons and the atoms, so the length of the wire, L, affects the resistance. Longer wires have more resistance. Now, something about the actual material ought to matter as well. And in terms of the material, we look at something called the resistivity, which is given the Greek letter that looks like a P, but it's actually called rho, R-H-O. And if you look in your textbook in section 11 or 13.1, I believe it is, on Ohm's law, you'll see the resistivity of various different substances. You remember that metals have low resistance, and look, they have low resistivities. Insulators have high resistance. These are very large numbers. Semiconductors, which are like what your computer chips are made of, have resistances somewhere in the middle, and they are very interesting. We'll talk more about them at a later date. However, we've now seen that there are three factors that affect the resistance of a wire. There is one other, and that is temperature. As we discussed earlier, the higher the temperature, the more the resistance. Now, this is a pretty complex dependence of temperature and resistivity. However, for substances at a constant temperature, we can write an equation, and the equation goes something like this. The resistance of a wire increases with length, so we should have L in the numerator. It increases with resistivity, so we should have rho in the numerator. But it decreases the bigger the wire gets, so it should have A pi r squared here. Sorry, I wrote that in a blue or an aqua color that's a little hard to see. It should have A pi r squared in the denominator. All right, so here's a formula for the resistance of a wire, and now I'm going to show you a calculation for that resistance. Here's a question out of your book, Physics 11 by Addison Wesley. A tungsten filament is used in an incandescent lamp. What is the resistance? So find the resistance, find the resistance R of that filament, which is a wire. It's the wire that you see in a light bulb if you look right over here. What is the resistance of that wire if we're using tungsten, which is 5 centimeters long and a diameter of 0.76 millimeters? So we're going to use L times rho over pi r squared. But they told us that the diameter was 0.76, so that is going to mean that the radius is 0.38 millimeters. And of course, we got to convert that into meters, so don't forget to do that. And then they've said tungsten. They haven't given us the resistivity, so we look down in this table here and we find tungsten resistivity 5.6 by 10 to the negative 8. So we're going to write down the length in meters times the resistivity, 5.6 times 10 to the negative 8. We're going to divide that by pi times r squared. 0.38 by 10 to the negative 3, that would be 3.8. I'm making this number 10 times bigger, so I've got to make that 10 times smaller. 10 to the negative 4. Don't forget to square. And if you do that, you should get a value for the resistance of the wire. I'm going to do that. Okay, and I get a value here, a pretty small value, it seems, of 6.2 times 10 to the negative 3 ohms, which seems like a low number, but then again it is a metal, tungsten, and metals tend to be good conductors. So there you go, there's a calculation of resistance of just a wire. All right, and the final slide. It's been a long video, or a long couple videos, but we've covered a lot of ground. We're finally going to talk about something we've already discussed in this course, which is called power. You remember what power is. Power is equal to the work done, or the energy used, divided by the time taken to do that. Well, same in an electric circuit, only we have different ways of calculating work or energy in a circuit. Do you remember how to do it? If you go way back to the very beginning, this is now a two-part video because I interrupted the video by accident, so go back to the first part and you will recall that the work or energy idea comes to us from voltage. If you remember, the voltage is equal to work divided by charge. So if I isolate W, that's going to be Q times voltage. So I can sub that in up here. Let's get going on that substitution. We've got QV, but now it's got to be divided by time. Now, what did we have to say about time? That, if you recall, was an idea that came from, sorry, just one moment, folks. Sounds like the phone is ringing. Okay, I'm back. It's been an eventful video, that's for sure. The time, how do we get at that? If you recall, the time factor in an electrical circuit is the current. I is equal to Q over delta T. So if I want to isolate delta T, I'm going to get Q over I. So in the denominator here goes Q over I. And then what happens? Well, this Q cancels with that Q. The over I comes up to the top. You get VI. And therefore, in the end, you end up with P equals VI. And that's it. That's the formula for the electric power in a circuit. It has the symbols that we're used to in electricity, voltage and current. Although back when we learned about power the first time, when we were talking about gravitational forces, we usually had to calculate work in some other way, maybe using an F delta D formula, if you recall that. Remember when we had work equals F delta D. Just a little note on that. When we haven't stopped using this, there are electric forces working. Remember, it's like the attraction or repulsion of electric charges, and charges do move through a distance in a circuit. so work is done. It's just that it's easier to calculate it now using terms like voltage, current, charge, time, etc. Anyway, that's fact number 4 of the video, this formula. And so we're going to finish off here with a practice problem, also from your textbook, Physics 11 by Nelson, and this one involves power and also the cost of electricity. So let's have a look. A vacationer uses 3 1,500-watt heaters to warm a cottage for 7 days, but the heaters are only on 25% of each day. So let's think for a moment. What is the power here? Power is equal to 1,500 watts. There are 3 of these things. They are on for 7 days, but only a quarter of each day do they operate. You don't need the heaters on every single minute. What's the so what we can do here is we can actually take the power, multiply it by all that time, and we're going to get what? Well, if you take the original definition of power, that power is equal to the work divided by time, then what I've done here, I've actually taken the power and I've multiplied it by an amount of time. This was the power, this was the time. So actually what I calculated for you here was not power times or on its own, but rather power times time. I'm sorry about that, I should have written that in. What is power times time? It's equal to work or energy, if you prefer. So this is actually E, the energy. Now let's calculate that. We got 1,500 watts times 3 heaters, 3 of those 1,500 watt heaters, times 7 days, but only operating for a quarter day. So I get 1,500 times 3 times 7 equals, and times a quarter, and that gives me 7,875. However, is this the right answer for the energy used? I hope you caught my mistake that I put in there. This is in days, and I've got to be in seconds, right? So if you recall, in one day there's 24 hours. Each hour has 60 minutes, and there are 60 seconds in a day. Should I go ahead and calculate the seconds, here's what I'm going to find. Times 24, times 60, times 60. I get a pretty huge number. In fact, it's so big that it's going to be hard to fathom how much energy was used. So if you recall, there was a unit of energy that we learned about a little while back that is a little bit more convenient when you're talking about electricity. We're not going to do our calculation this way. Here's what we're going to do. See if you can figure out what I'm up to here. 1,500 watts is 1.5 kilowatts. And because these are being used for 7 days, which is 7 times 24 hours, how many hours is that? 7 times 24, that gives us 168 hours. However, we also have to divide by 4 because it's only used a quarter of the day. So divide by 4. We now end up with 42 hours. So guess what? Remember, see where I'm going with this? That's 1.5 times 42. This is in kilowatts. That's in hours. What does that give me? It gives me 63 kilowatt hours of energy. Isn't that a much nicer number to deal with than what you were about to get over here if you were using joules? So 63 kilowatt hours. The cost is 20 cents per kilowatt hour. So if something is costing you 20 cents and you're using or consuming 63 of them, what do you got to pay? As it turns out, not a heck of a lot. 1,260 cents, or $12.60. All right, so there's a calculation. This is the kind of calculation homeowners have to deal with when they're running electrical appliances and they are charging up or racking up an electricity bill. 20 cents per kilowatt hour is a little high these days. We don't pay that much here in Ontario. We probably pay closer to half that, but still it can add up. Anyway, that's it. We've now covered all the basics, all the beginning part of this unit. all in a couple videos. So make sure you understand the 4 facts of the day or of the video, and you understand these calculations, and I will see you guys in class. Thanks for watching.